Hello students, this is Dr. A.S. Iyer. I welcome you all for the course on finite element method in civil engineering. Our today's topic is how to write down displacement function or polynomial function for finite elements. We know that in the step-by-step procedure of finite element analysis, in the very first step after discretization, we have to represent the approximate variation of displacement. So today in this class we will see that how to write down that approximate variation of displacement using polynomial expansion. So very first element is two-noded bar element. So if you remember your strength of material, in bar structures are normally subjected to axial forces. It may be axial tensile or axial compressive, right? So bars are subjected to axial tensile or axial compressive forces. So because of these axial forces, each point of the bar is subjected to axial displacement. It means bar may get elongate if it is a tensile force, or bar may get compressed if it is a compressive force. So only all points will shift horizontally in the direction of force, because bar is a one-dimensional element. So it means at each node of the bar element there is only 1 degree of freedom, which is called as axial displacement. Since bar is one-dimensional element, if you assume that bar is in x coordinate, x direction only, in x direction displacement we are representing by u, right? And that's why at node number 1 displacement is u1, and at node number 2 displacement is u2. So remember, in the bar structure or bar element, total degrees of freedom are equal to 2 if there are 2 nodes. So at each node there is one unknown, right? So since there are 2 nodes, total degrees of freedom are 2. So it means total degrees of freedom are 2. So we have to select 2 elements from Pascal triangle to write down the displacement function for 2-noded bar element. You have to select 2 elements from the Pascal triangle to write down the displacement function of bar element. Now since bar element is a one-dimensional element, if it is a horizontal bar element representing only x direction, or sometimes if bar element is a vertical, it represents only y direction, right? It means either x or y. We have to select only x or y coordinate from the Pascal triangle. We cannot select both at a time, either x or y. So how many elements we have to select? 2 elements from the Pascal triangle. Why 2 elements? Because total degrees of freedom are 2. Why total degrees of freedom are 2? Because there are 2 nodes, and at each node there is 1 degree of freedom, which is called as axial displacement, right? So 2 elements we have to select from the Pascal triangle. So this is the Pascal triangle. 2D Pascal triangle we will use to write down the displacement function of 2-noded bar element. So 2 elements from the Pascal triangle. First element is 1. That is a constant term. Of course we have to start from the top first row. So first element is 1. Now if you shift to second row of Pascal triangle, we have 2 options, either x or y, right? But now since our bar element is horizontal in x direction only, we have to select only x coordinate. We cannot select y coordinate. If that bar element is vertical in direction, we can select y also. In that case we have to select only y, not x. So at a time either x or y we can select, because bar is a 1D element. So since we have to select the 2 elements from the Pascal triangle, so first element is 1, and out of these 2 the second element will be x, right? So displacement function can be represented like this. If you select any point on this bar element, any point, the displacement of this point is, let it be u. So we are writing displacement of any point on the bar element is u. Now we have to add these two elements together. So it represents 1 plus x, right? 1 plus x, where 1 represent actually constant term and x represent that it is a linear term. But remember, this 1 represent the constant, which means it is not necessary that it is always 1. It may be 2, 3, 4, 5, any constant number. And in the second term, x represent that power of x, degree of x is 1. But always it is not necessary that coefficient of x is always 1. So this 1 plus x can be 2 plus 2x, 2 plus 3x, 3 plus 4x. It means, understand, this 1 represent the constant, first term represent the constant, so it may be any constant number. In second term, this x remains as it is, x raised to 1, but coefficient of x may be 1, 2, 3, 4. Right? We don't know what is that coefficient is. Right? So whenever we write down the displacement function, only this 1 and x are not sufficient. We have to multiply with this variable some unknown generalized coordinates. Let it be alpha 1 and here alpha 2. The generalized coordinates. So alpha 1 and alpha 2 needs to determine using the mathematics. Right? So alpha 1, alpha 2 represent that unknown generalized coordinates. Why we have used alpha 1 and alpha 2? Because first term is constant, means it is not necessarily always 1, it may be 2, 3, 4, any constant number. So alpha 1, value of alpha 1 represent that constant number. And in the second term, it is not always x, it may be 2x, 3x, 4x, 5x. So that coefficient of this x is represented by alpha 2. Now we have to add this 2 which represent the displacement function. So finally displacement function or polynomial function for two noded bar element is u equal to, what u represent? U represent displacement of any point of the bar is u. So this alpha 1 into 1, alpha 1 into 1 means alpha 1 plus alpha 2 into this x is alpha 2x. So u is equal to alpha 1 plus alpha 2x. This u represent approximate variation of displacement of any point of the two noded bar element. Okay, so this is displacement function. Similarly, we can discuss the displacement function of other elements, like if you increase one more node in the bar element, if it is a 3 noded bar element. Okay, so 3 nodes are there. So total at each node there is 1 degree of freedom, that is displacement in x direction, u1, u2, u3. Now there are 3 nodes, so total degrees of freedom are 3. Right, total df are 3. It means we have to select the 3 elements from the Pascal triangle. Okay, again remember, since it is a bar element, we have to select only x coordinate or only y coordinate from the Pascal triangle, right? Because it is a 1D element. So this is Pascal triangle again. Now how many elements we have to select? 3 elements, right? So first element is 1, second element is x. Of course we cannot select y because it is a horizontal bar element. Then we have to shift to third row for the third element, and in this we cannot select these 2 elements because here it is a y coordinate, so we have to select the x square, right? Then we have to multiply by generalized coordinates to this alpha 1, here it is alpha 2, here it is alpha 3, and then we have to add all these 3 together to write down the displacement function for 3 noded bar elements. So it is u equal to alpha 1 into 1, that is alpha 1, then alpha 2 into x, it is alpha 2x, and alpha 3 into x square, it is alpha 3 x square. Of course, if it is a vertical bar, then we can write down this u is equal to alpha 1 plus alpha 2y plus alpha 3y square. Like this also we can write down this. So either we can use x or we can use y. We cannot use both because first element as well as the second element, both are one dimensional elements. Okay, so this is three noded bar element. Third element is two noded beam element. So if we are using the beam element to discretize the continuous beam, so two noded, if you assume this node is node number I and this node is node number J, we know that in the types of element we had discussed, in the beam element at each node there are 2 degrees of freedom. One is vertical translation, which is called as vertical displacement, and second is rotation. Okay, so this is W and this is theta. We can write this is W1, theta 1. This is W2, that is vertical 3 means W2 and 4 means theta 2. So W1, theta 1, W2, theta 2, total degrees of freedom are 4 in beam element. Okay, here df per node are 2. Okay, total degrees of freedom are 4. Now remember, since beam is a bending element, this theta 1 and theta 2 are not primary unknowns. This theta 1 and theta 2 we can determine if we know the deflection. If we know W is a deflection, dW by dx is the slope, that is theta. Right? This is equal to theta. It means theta is not an unknown actually. If we know W, we can determine the theta. So in the beam bending element, actually unknown displacement is only deflection, only W. So theta we can find out by differentiating the W with respect to x. So in beam element displacement we have to consider only W, not theta. So to write down that W deflection, we have to select 4 elements from the Pascal triangle. Why 4 elements? Because total degrees of freedom are 4. Right? Why total degrees of freedom are 4? Because at each joint or node there are 2 degrees of freedom. So total degrees of freedom are 4. Okay. So again we will consider this same Pascal triangle 2D. Now 4 elements we have to select from this. So first element is this one. Out of remaining 2, second row, we will select x only, because beam is also one dimensional structure having only length that in x direction. So we will select only x. From third row we will select only x square, because we cannot select y and y square. So these terms we will discard. 1x x square. From the next row we will select the x cube. So because in these 3 we are having y coordinate. So 4 elements we have selected from the Pascal triangle, and those elements are 1x, x square and x cube, which are again multiplied by generalized coordinates alpha 1, alpha 2, alpha 3 and alpha 4. Now we have to add all these 4 elements together to write down the final displacement function, and that displacement function is in terms of only W. So W is equal to alpha 1 into 1 plus alpha 2x plus alpha 3x square plus alpha 4x cube. This is the displacement function for 2 noded beam element. Now there is one more important point to be remembered in these 3 elements. First was 2 noded bar element, then 3 noded bar element, right? And now 2 noded beam element. So in all these 3 elements, the symmetry of Pascal triangle is disturbed because of these 3 are 1D elements, and we cannot select y in the displacement function. Just because of this, in all these 3 elements, the symmetry of or axis of symmetry is disturbed. But when you write down the displacement function for 2D elements, you have to take care that axis of symmetry must be maintained. So we will see some examples of 2D elements also. So first 2D element is constant strain triangular element. Constant strain triangular element, which is also called as CST element. So in CST element, number of nodes are 3 at 3 corners, right? So at each node there are 2 displacement. Displacement in x direction, which is represented by u, and displacement in y direction is represented by v. So at each joint there is u1, v1, u2, v2 and u3, v3, two displacement. Now remember, since it is a two-dimensional element, displacements are in two directions, x direction and y direction. So displacement in x direction, if you select any point on this triangle, so displacement of this point in x direction is represented by u, and displacement of the same point in y direction is represented by v. So we have to consider the degrees of freedom in x direction and y direction separately, because it is a 2D element having two displacement u and v. That's why if you look at here, degrees of freedom per node are 2. Total degrees of freedom are 6. Out of this 6, 3 in x direction and 3 DOF are in y direction. So these 3 DOF in x direction are used to represent the displacement u, and these 3 in y direction used to represent the displacement v. Right? So we have to write down displacement function for u separately and v separately in 2D elements. Okay, so this is the Pascal triangle. Now understand, to write down the displacement function u, we have to use 3 elements from the Pascal triangle, because degrees of freedom in x direction are 3, u1, u2, u3. And similar 3 elements we have to use to represent the displacement v, because unknowns are v1, v2, v3. So now 3 elements we have to select. Now understand, this is 2D element, and now we have to take care that we have to maintain the axis of symmetry, because we can select x as well as y coordinate from the Pascal triangle. Since it is a 2D element having x and y both coordinate, we can select both x and y coordinate from the Pascal triangle. So now which 3 element we should select? First one is 1, and from second row it is x and y. Right? So total are 3 elements. All these 3 elements are multiplied by generalized coordinates alpha 1, alpha 2 and alpha 3. Then we have to add these 3 together to write down the displacement function. So what is the displacement function for CST element? This is alpha 1 into 1 plus alpha 2 into x plus alpha 3 into y. This is u. Right? Now similarly, to represent the v displacement function in y direction, we have to consider the degrees of freedom in y direction. So degrees of freedom in y direction are also 3, v1, v2, v3. So to represent the v also, we have to select the 3 elements from the Pascal triangle, and those 3 elements are same, 1, x and y. 1, x and y. But of course, the generalized coordinate, since already we have used in u alpha 1, alpha 2, alpha 3, to represent the v, we will use the different generalized coordinates. Let it be alpha 4, alpha 5 and alpha 6. Alpha 4, alpha 5 and alpha 6, which are multiplied to these 3 terms. And then we have to add these 3 together. So v equal to alpha 4 plus alpha 5x plus alpha 6y. So there is a separate displacement function for u, that is displacement in x, and separate displacement function for v, that is displacement in y. Next element is linear strain triangular element, LST element. Linear strain triangular element. The only difference in CST and LST is, that is constant strain triangular element and linear strain triangular element is, in CST there are only 3 nodes, in LST there are 6 nodes. So in addition to 3 corner nodes, there are 3 more nodes at the center of edges of triangle. So look at here, this is 1, 2, 3 at the corners and 4, 5, 6 at the middle of these 3 edges. So total degrees of freedom now, there will be u1, v1 to u6, v6, right? u1, v1 to u6, v6. So at each node there are 2 unknowns. Total degrees of freedom will be 12 because there are 6 nodes. Out of these 12, 6 displacements are in x direction and 6 degrees of freedom in y direction. So x direction is represented by displacement u and y directional displacement is represented by v. If you select any point in this triangle, its x directional displacement is u, y directional displacement is v. It means to write down the displacement u, we have to consider the 6 degrees of freedom in x direction, that is u1 to u6. So we have to select 6 elements from the Pascal triangle, right? It is also 2D element, so we can select x and y coordinates both. Now if you look at this is 1 first term, then 2, 3, then 4, 5 and 6. So these 6 elements we have to select. We have to multiply these 6 elements by generalized coordinates alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 and alpha 6. So u is equal to see alpha 1 plus alpha 2x, alpha 3y, alpha 4x square, alpha 5xy, alpha 6y square. Similarly, there are 6 degrees of freedom in y direction, that is v1 to v6. So we have to select 6 elements from the Pascal triangle which are same 6 elements, but of course generalized coordinates multiplied to these 6 elements will be different. So v is equal to, instead of alpha 1 to alpha 6, now we will use alpha 7, alpha 8, alpha 9, alpha 10, alpha 11 and alpha 12. These elements are same from which are from the Pascal triangle. Right? These elements are same. Generalized coordinates multiplied to that are different. Alpha 1 to alpha 6 for u, alpha 7 to alpha 12 for v. Right? This is LST, linear straight triangle element. Then we can consider the rectangular element now. It is called as 4-noded rectangular element. Now, since there are 4 nodes and at each node there are 2 unknowns, x directional displacement u and y directional displacement v. So total unknowns will be 8, which are called as total degrees of freedom. Out of 8, 4 degrees of freedom in x direction, 4 degrees of freedom in y direction. Displacement in x direction is equal to u, displacement in y direction is equal to v. So now we have to write down displacement function for u and v for these 4-noded rectangular elements. So we have to select 4 elements from the Pascal triangle now. For u1 to u4 and for v1 to v4, we have to select 4 elements. Now see how to select those 4 elements. 1, x and y. First 3 elements, these are 3. Now we have to select last one, that is 4th one. But if we shift to next row, there are 3 options. We have 3 options, x square, xy and y square. And we have to select only one element from out of 3. So which element we should select? That element is xy. So what is the criteria to select this? If we have an option from number of elements, we have to select 1 or 2. So there is one important property of this Pascal triangle, that while selecting the element, axis of symmetry should not disturb. That is one of the important criteria to use the Pascal triangle, and that is axis of symmetry or symmetry of triangle should not disturb. Which means if you select the x square as a 4th element, the right part of the triangle will be having the more elements, that is x, y and y square. If you select the y square as a 4th element, then left portion of the left part of the Pascal triangle will be having more element. If you select xy as a 4th element, now if you see on the both side, similar number of elements will present, that is 1 1, x square and y square. It means if you select xy, the axis of symmetry will be maintained, and that's why the 4th element will be xy. So which 4 elements we have to select from the Pascal triangle? 1, x, y and 4th one is xy. So these 4 elements will be multiplied with the 4 generalized coordinates alpha 1, alpha 2, alpha 3 and alpha 4. And if you add these together, that will be displacement function, which is alpha 1 into 1 plus alpha 2x plus alpha 3y plus alpha 4xy. Now since same 4 degrees of freedom are in y direction, v1 to v4, we have to select again 4 elements from the Pascal triangle. Those elements remain same. These 4 elements remain same. only multiplying generalized coordinates will be different for V. Alpha 1 to alpha 4 already we have used for U. So for V we will use alpha 5, alpha 6, alpha 7 and alpha 8. Right? So these are the displacement polynomial or displacement function for 4-noded rectangular element. Now 4-noded rectangular plate bending element. Now it is bending element. Understand. Bending represent, already we have discussed one bending element, that is beam bending element. So if it is a bending means what? If you consider this is a plate or slab and load is acting perpendicular to this slab will bend, right? So this is called as bending element, and whenever structure will bend, the unknown will be rotation. Okay, so that's why it is called as plate bending element. So in bending element, at each joint there are three unknown. One is vertical translation, that is called as vertical deflection at each joint. And since this element will bend, if you look at this corner, suppose this will bend like this and this edge will bend like this. So there is a rotation of two edges, this one and this one, right? So that rotation is called as theta x1 and theta y1. Rotation in x direction and rotation in y direction. So at each joint there are two rotation and one deflection. So three unknown. There are total 4 nodes in this plate bending element. So total degrees of freedom will be 12. Okay, at per node it is 3, W, theta 1 and theta 2. Total nodes are 4. So total degrees of freedom are 12. Now in bending element it is similar to beam. Theta 1 and theta 2 are not primary unknowns. If we know the polynomial of W, if we know the polynomial function of W, we can find out theta 1 by differentiating W with respect to X, and we can find out theta 2 by differentiating W with respect to Y. So theta 1 and theta 2 are not unknown. If we know the deflection, we can find out rotations. This is bending element, and that's why here also we will represent the displacement function for only W, not theta 1, theta 2. Okay, so all total 12 DOF means 12 elements from the Pascal triangle we have to use to represent only W, right? So 12 elements now. 12 elements we have to select from the Pascal triangle to write down the displacement function for plate bending element. So this is Pascal triangle now. We have to select 12 elements. Please understand now which 12 element we should select. 1, 2, 3, 4, 5, 6. There are 7, 8, 9, 10. Okay, so total 10 here. Now we have to select remaining 2, and we have in the next row 5 options. So which 2 we should select? Okay, so we have to take care that the first point which we have discussed, axis of symmetry should not disturb. Symmetry of triangle should not disturb. So to maintain the symmetry of triangle, we have to select either these two, x raised to 4, y raised to 4, these two element, or we have to select this x cube y or xy cube. We have two options again now. Either we can select these two elements, remaining 2, or we can select this x raised to 4 and y raised to 4. So while selecting, if you are having two options, then again the next one more property of Pascal triangle comes in picture, and that is always select elements which are nearer to axis of symmetry. If this is axis of symmetry, so nearest element to this axis of symmetry is this. So always select element which is nearer to axis of symmetry. So we should select these two elements, and these 10 elements total becomes 12, right? And all these elements will be multiplied by generalized coordinates. So this is final expression of W. Alpha 1 into 1, alpha 2x, alpha 3y, alpha 4x square, alpha 5xy, alpha 7y square. Alpha 6y square, sorry, alpha 7x cube, alpha 8x square y, alpha 9xy square, alpha 10y cube, plus alpha 11x cube y, plus alpha 12xy cube. This is displacement function for 4 noded rectangular plate bending element. Okay. Now next we will see one example of 3D element also. 4 noded tetrahedron element, which is 3D element. So if it is a 3D element, we have to use 3D Pascal triangle. So there are 4 nodes. At each node there are 3 unknowns: x directional displacement u, y directional displacement v, and z directional displacement w. So total nodes are 4. Per node unknowns are 3, that is u, v, w. So total degrees of freedom are 12. But out of these 12, 4 degrees of freedom are in x direction, 4 degrees of freedom are in y direction, and 4 degrees of freedom in z direction. So displacement in x direction is represented by u, displacement in y direction is represented by v, and displacement in z direction is represented by w. Right? So we have to select 4 elements for x, 4 elements for y, and 4 elements for z directional displacement from 3-dimensional Pascal triangle. 3-dimensional Pascal triangle. So this is 3-dimensional Pascal triangle. Now we have to select 4 elements for x. So it is 1, 2, 3 and 4. So first 4 elements to represent the displacements. Now these 4 elements will be multiplied by generalized coordinates alpha 1 to alpha 4. So displacement u is equal to alpha 1 into 1 plus alpha 2x plus alpha 3y plus alpha 4z. Then similar to this u, same 4 element but different generalized coordinate alpha 5 to alpha 8 we are using for v, and alpha 9 to alpha 12 for w, where 4 elements from Pascal triangle are same, that is x, 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 y, 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 z, 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 and here it is 1. Right? So u, v, w are the displacement functions for the 4 noded tetrahedron element. So like this we can represent the displacement function or polynomial function by using Pascal triangle. These are the few elements we have discussed, 8 elements, but of course we can write down displacement function of any element if your concept is clear. Okay, I hope all of you understand how to write down the displacement function or polynomial function for the finite elements based on degrees of freedom and using Pascal triangle. Okay, in the next class we will discuss the next article of this course, finite element method in civil engineering. Okay, thank you very much.